hard enough for us to build a bionic hand that's fast, has touch feedback, and is easy to use. It's even harder for us to build one for Dan, who's really going to be putting it through the ringer. So we had to come up with a test that would show that the hand is strong enough to survive Dan. So we thought, arm wrestling. If it can survive arm wrestling, it can survive anything. Here's how it'll work. We're gonna put our elbows on the table and assume, a natural position for arm wrestling. So we'll grip it just like this, and then he'll use his muscles to make a power grip around my wrist. And so we'll just go at it at that point. And as we're doing this, right, all the forces are going to be placed on this wrist joint here. So we had to redesign the wrist to be able to withstand those kinds of forces. The tricky thing about this wrist is that it has to be able to rotate and disconnect from the socket. And so that makes the engineering problem a lot harder. To test how much force it actually takes to arm wrestle, we built this load testing setup. I'm going to put my hand through it and then pull against it, and it's gonna actually tell us how much force that I'm applying.
I have this ratchet here that's bolted down to a stronger piece of aluminum. The rope is attached to the load tester, and the tester is attached to the ability hand. 137 pounds.
Dan's going to have a little bit of an advantage here because his wrist is going to be metal and mine's actually flexible. So his is going to be stiffer as we go at it in this arm wrestling competition, right? But his residual limb only goes up about halfway on this socket. And the further away the hand is from his residual limb, the longer that lever arm is going to be and the harder it is to produce the torque needed to beat me in an arm wrestling match.
Physics and physiology of an arm wrestling match are pretty complicated, but you can simplify it down to a fairly straightforward physical model without losing too much information, especially if you're going to be focusing on a factor like forearm length. You might know this equation. Torque is equal to perpendicular force times perpendicular distance. Accordingly, you can rearrange and find that the force, which is going to be felt here at the middle, is going to be equal to the torque divided by the perpendicular distance. We find that the perpendicular distance with your elbow 90 degrees is equal to the length of your forearm. Now, with two forearms of the same length and two people putting out the same amount of torque, you're going to find you end up with the exact same amount of force in the middle. It's a tie. But if you increase the forearm length for someone, as we did with increasing the length of the socket, you also increase the length of the lever arm perpendicular to the axis of rotation. Longer distance, smaller force means a one-sided competition. And the only way to get that force back up again is to increase the torque.
Podcast.